Projectile motion. A projectile is an object thrown in the presence of gravity. Gravity will be the only accelerating force, or the only force acting on the object. We're going to ignore air resistance for now. I mean, there's a lot of things that are projectiles: baseballs, footballs, golf balls. We're not talking about propelled objects like airplanes, but something that's thrown without a motor. Here's the important idea, or one of the important ideas, one of the most important ideas about projectiles, and that is the horizontal and vertical components of the velocity are independent of each other. They do not affect each other. The horizontal velocity is constant motion, or constant velocity. So there's no acceleration. The acceleration is 0. However, the vertical velocity is changing. It's changing due to gravity. The acceleration is negative 9.81 meters per second squared. Now, a lot of times, as before, we're going to round it off to negative 10 meters per second squared. All right, so I'm going to give you a little illustration here in a second, but we're going to launch a ball at an angle. And we don't need to worry about the angle so much right now, but there's a vector that represents something being thrown at an angle. And we're going to call that vector v, or velocity v. And just like we've been doing for the last few days, we have components. If I draw my x component and my y component, well, I can draw the box like we've been doing. I'm going to call this x and y, consistent with the x and y axes in coordinate graphing. X is the x component, like we talked about. The x component will be constant. The velocity doesn't change in that direction because gravity doesn't work that way. Gravity works up and down. Y and v are changing. The vector y is changing because of gravity, which then affects vector v, but x will stay constant. So let me give you a little example in illustrated form here on the next page. So this diagram could represent, it's a motion map of a ball. Let's say it's a golf ball that's being chipped onto a green. And each little dot here represents the golf ball in 1 second intervals. So the time between each frame is 1 second. So the ball that I have mapped out already here in blue is upon initial impact at the ground. And let's say, this diagram is like the one I just had a few minutes ago, or a few seconds ago, that the horizontal velocity of the ball is 10 meters per second. And the vertical launch speed is 30 meters per second. Now, these could be any numbers, but I just made up some nice numbers to work for us here. And if we want to figure out, though, the actual vector itself, we're going to call that v. I'm not drawing a rectangle here, but it's the same kind of rectangle. Just imagine a rectangle like we were using for the last couple of days. But if I want to figure out vector v, it simply is going to be v squared equals 10 squared plus 30 squared, because v is the diagonal of a rectangle or the hypotenuse of a triangle. So if you solve this, I'm going to do it on my calculator, you will get the square root of 1,000, which is 31.6 meters per second. So that's the actual launch speed of the golf ball. Now, after 1 second, the golf ball is here. I'll use red now. And what's happening is the golf ball is still moving sideways at 10 meters per second, because once again, gravity doesn't work that way. Gravity works up and down, slowing down the vertical component to 20 meters per second. So I'm drawing that a little shorter now. All right, so the vertical velocity went from 30 to 20 because you slow down at a rate of 10 meters per second each second. So the actual velocity now is like around that way. Once again, you don't need to draw the rectangles right now. But if I wanted to find v, I'm going to call this now v1 for the velocity at 1 second. v1 squared is 10 squared plus 20 squared. So v sub 1 will be the square root of 500, which is 22.4 meters per second. We can go to 3 sig figs here for better illustrative purposes. 22.4 meters per second. Well, the ball is slowing down from 31.6 to 22.4. It keeps slowing down, except in the horizontal direction. So, next case, I'll go back to blue. This ball right here is the 2-second mark, but once again, the ball is still going sideways at 10 meters per second. But vertically, it has slowed down also to 10 meters per second. Once again, slowing down at the same rate as it has been the whole time because of gravity. So that's the overall, I'm going to call that V sub 2, the velocity at the 2-second mark. V sub 2 squared will be equal to 10 squared plus 10 squared. Plug in your calculator, take a square root. V sub 2 for the 2-second mark is, I believe, 14.1 meters per second. When it gets to the very top spot, now it takes 3 seconds to get to the top, just like we've talked about before, and the reason being is that it's slowing down at 10 meters per second each second. It's just like throwing a ball straight up. It would lose all its speed in 3 seconds by losing 10 meters per second each second. But it's still traveling sideways, so it never comes to a stop. This ball is still traveling sideways at 10 meters per second. So we could say V sub 3 is 10 meters per second. It'll never come to a dead stop up there because it's always moving sideways. Now it starts to come down and it repeats the process symmetrically. When it gets to this spot, I'm going to go back to blue. It gets to this spot, this is the 4-second mark. It's still going 10 meters per second sideways. That's meters per second. And it's moving 10 meters per second downward. So it's, once again, has a diagonal speed or a hypotenuse speed of, well, it's the same as it was at V sub 2, or V at 2 seconds. That V sub 4 is going to equal 14.1 meters per second, because it corresponds to the other point 1 second before it gets to the top. This is 1 second after the top because it's symmetrical. Going back to red, ball is traveling at 10 meters per second sideways, but now it's gaining speed. It's going 20 meters per second vertically, but it's supposed to be a vector, straight line arrow. But I'm going to call that V sub 5 for the 5-second mark. Is going to be the same as V sub 1, the 1-second mark. It's 22.4 meters per second. That's 22.4 meters per second. And then upon impact, way over here, that's when the ball hit the ground, not after it embeds in the ground or bounces. It's hitting the ground just as it hits the ground. Just as it hits the ground. It's still traveling 10 meters per second. And if it's a golf ball, it's going to make a pretty good divot. If you've ever played golf, it's always fun to make good divots when you're playing golf. That's the mark of a good golfer. But the vertical component, it's getting a little messy here, and I can't really erase this. But that blue vector I just drew is 30 meters per second. I'll use black here just to kind of highlight those two. There we got the 10 and the 30. So the impact speed, I'm going to call that V6 because it takes 6 seconds for this ball to get all the way through its flight, just as if you had thrown it straight up. It would have taken 3 seconds to go straight up, 3 seconds to come straight down. It still was 6 seconds in the air. That is going to be the initial speed of 31.6 meters per second. So that's our final impact speed. Now, interestingly enough, it's traveling sideways the whole time. You could actually figure out how far this golf ball went if it's actually, hitting on the green exactly where you wanted it to. Because horizontally, there's no acceleration. All you would be using is V equals D over T, where horizontally, the ball is traveling at the 10 meters per second. Horizontally, it's traveling at 10 meters per second. I'm going to plug in 10 for V. You're looking for D, the horizontal distance, and the time is 6 seconds. It's in the air for 6 seconds. So D, the horizontal distance it travels, is 60 meters, which is, well, it's about 65 yards, let's say. 60 to 65 yards. And that's a little chip shot in golf.